In this video, I will be talking about exponential growth and decay. So first off, I'm going to start with the differential equation dy over dt equals k times y. And this is a differential equation because we have y prime and y in the same equation. So this is saying that the rate of change of y with respect to t is proportional to y itself. So here we can multiply top and bottom by y to get the y's on the same side, and then multiply top and bottom by dt. So I just cross multiplied these terms, and now I can integrate these two. And the integral of 1 over y is ln y. And the integral of k dt is kt plus c. And I only need the constant on one side here. And now I'm going to take the exponential of each side. So I'm going to get y equals e to the kt plus c. And this is the same as e to the kt times e to the c. So e to the c is just another constant. So I can write this as y equals c times e to the kt. But now when I plug in t equals 0, I can get my initial value. So I get y of 0 equals c times e to the 0. And e to the 0 is 1. So c just equals y of 0. And sometimes this is written as y sub 0 or y naught. So now my final equation is y of t equals y naught e to the kt. And k is just your constant. So these are the two formulas that we're going to be using for all of these exponential equations for exponential growth and decay. So we started off with the differential equation here, and then we derived the y of t function. And now there are a few applications of exponential growth and decay. One of them being population growth. And the differential equation for that is dp over dt is equal to kp, which means the growth of the population is proportional to the population size. So then our equation for this is p of t equals p naught times e to the kt. So here this is the same as the differential equation that we began with. We just have different variables. So instead of y, we have capital P. Instead of y naught, we have p naught. Now a second way we could use exponential growth or decay is through radioactive decay. Or in other words, a half-life problem, where we have a certain substance that reduces over time. So here we have dm over dt is equal to km, where m is equal to the mass of the substance. And then our m of t will equal m naught e to the kt. So once again, these are the same equations, just different variables. Now the last one I will be going over is Newton's law of cooling. And this law states that the rate of change of the temperature is proportional to the temperature minus the surrounding temperature. So T sub S will be our surrounding temperature. Population growth problem. A bacteria culture initially contains 100 cells and grows at a rate proportional to its size. After an hour, the population has increased to 420. So if we know we're going to use the equation P of t equals P naught times e to the kt, we initially have 100 cells. So we know our P naught is equal to 100. And then if t is our hours, then after 1 hour, we have 420 bacteria. So plugging this into the equation, we have 420 equals 100 times e to the kt. And since t is 1 here, this will be just k times 1. Now we will divide 100 from each side and we get 4.2 equals e to the k. And so k equals ln 4.2. So now it's asking for the expression of the population after time t. So we will get P of t equals 100 times e to the ln 4.2 times t. But as we know, if we have e to the a times b, that's the same as e to the a to the b power. So we can rewrite this as 100 times e to the ln 4.2 to the t power, and the e and the ln will cancel. And then we're left with 100 times 4.2 to the t as our P of t. Next part of the question, they're asking how much bacteria is there after 3 hours. So we will just plug in P of 3. We get 100 times 4.2 to the 3, which is approximately 7,408.8 bacteria. And the next question asks, when will the population reach 10,000? So here we have P of t equals 10,000. Find t. So we have 10,000 equals 100 times 4.2 t. We're going to divide 100 from each side. We will get 100 equals 4.2 to the t. And now since t is our exponent, we're going to take the natural log of each side to bring that exponent down. So then I have ln 100 equals t times ln 4.2. Now I'm going to divide ln 4.2 from each side. And I get t equals ln 100 divided by ln 4.2. And that is approximately 3.209 hours. So after 3.209 hours, there will be 10,000 bacteria. Okay, now for my next example, I have radioactive decay. So for this one, we have the equation y of t equals y naught e to the kt. The half-life of cesium-137 is 30 years, which basically just means that this substance will reduce to half of its size after 30 years. And suppose we start off with a 100 milligram sample. The The first question asks to find the mass after t years. So here they just want us to find this y of t equation. So we know that if we start with 100, and in 30 years we get half that amount, which is 50, and then the half-life is 30 years, we'll have e to the 30 times k as our equation. Now we can divide 100 from each side, and we get 0.5 equals e to the 30k. Then we can take the natural log to each side, and we will get ln 0.5 equals 30k. And then finally we can divide 30 from each side. So we get ln 0.5 equals, or k equals ln 0.5 divided by 30. And this is the same as ln 1/2 over 30. So if we bring a negative 1 to the front, we can make this negative ln 2 over 30 as our k, because 1/2 is really just 2 to the negative 1, and when we have an exponent, when we have a power, we can bring that to the front with logs. So here, this is our k. So now we just have to plug this into our equation. So we have y of t equals the initial value, which was 100, times e to the k, which is negative ln 2 divided by 30 times t. So now we can write this as 100 times e to the ln 2 times negative t over 30. And once again, since we have multiplication in our exponents, we can write this as e to the ln 2 to the negative t over 30. The e and the ln will cancel, so we get 100 times 2 to the negative t over 30 as our y of t. So once again, that's y of t equals 100 times 2 to the negative t over 30. How much is left after 100 years? So here we're just going to plug in y of 100 into our equation. So we have y of 100 equals 100 times 2 to the negative 100 divided by 30. And then plugging that into our calculator, we're going to get about 9.92 milligrams. Now the last question, it says, how long until there's only 1 milligram left? So now we're going to set the equation equal to 1. So we have 1 equals 100 times 2 to the negative t divided by 30. We're going to divide 100 from each side. Then we get 2 to the negative t over 30. And now we're going to take the log of each side to bring this exponent down. So we get ln of 1 over 100 equals negative t over 30 times ln 2. And finally, we can multiply 30 to each side and divide by ln 2, and also multiply by negative 1 to get rid of that. So we get t equals negative 30 times ln 1 over 100 divided by ln 2. And then t will approximately equal 199.3 years. A roast turkey is taken from an oven when its temperature has reached 185 degrees Fahrenheit and is placed on a table in a room where the temperature is 75 degrees Fahrenheit. So here we have the equation. D over dt equals k times T minus the surrounding temperature. And our surrounding temperature is 75 degrees Fahrenheit. And our initial temperature is 185 degrees Fahrenheit. So here, if we multiply T minus Ts to both sides, we can solve for this differential equation. And then take the integral of each side. So we get ln of T minus Ts equals kt plus c. Then we have e to the kt plus c equals T minus Ts. And since this is a constant itself, we can bring that down. So we have c times e to the kt equals T minus Ts. Equals the initial temperature minus the surrounding temperature here. So our C is equal to 185 minus 75, which is 110. So now we have 110 e to the kt equals T minus the surrounding temperature, which is 75. Now the first question asks, if the temperature of the turkey is 150 degrees after half an hour, what is the temperature after 45 minutes? So they have after 30 minutes, the temperature is 150 degrees, and they want to find out what is the temperature after 45 minutes. So here, since we had 110 e to the kt equals T minus 75, we can plug in 150 for our T, our capital T, and then for our minutes, it's 30 minutes, so we'll plug that into here to solve for K. So we get 110 equals 110 times e to the 30k equals 150 minus 75. That gives us 110 e to the 30k equals 75. And we can divide 110 from each side. And now we have everything we need to solve for the temperature after 45 minutes. So we have 110 e to the 1 over 30 times ln 75 over 110 times 45 minutes is equal to the temperature minus 75. And here once again we can rewrite this as e to the ln 75 over 110 times 45 over 30 equals T minus 75. So we get 110 times 75 over 110 to the 45 over 30 equals T minus 75. And now plugging this into your calculator, you get that T is approximately 137 degrees Fahrenheit. And the second question asks, when will it cool to 100 degrees Fahrenheit? So here we want to solve for T when capital T equals 100. So my equation is 110 e to the 1 over 30 times ln 75 over 110 times T equals capital T minus 75. And so my capital T here is 100. And then I can rewrite this as 110 times 75 over 110 to the t over 30 equals 25. And now I can divide 110 from each side. And I get 75 over 110 to the t over 30 is equal to 25 over 110. At this point, I can take the natural log. So I get t over 30 times ln 75 over 110 equals ln 25 over 110. And now I'm going to multiply each side by 30 and divide by ln 75 over 110. So I get 30 times ln 25 over 110 divided by ln 75 over 110. And so our t is approximately 116 minutes.